For 5.2, we are going to move on from a transformation, which was the inverse transformation, which we learned last day, and we're going to start introducing a new type of function. So now we're going to be looking at exponential functions and the graphs of exponential functions. So before we can talk about graphing, I want to define what an exponential function is. So an exponential function is anything that has a variable in the exponent. And the exponent, of course, has to be a real number. But there's also restrictions on what the base of this power can be. So the base A can be something like 3 or a half or 3.52, but what it can't be is negative or 1. So here's my first restriction. The base A has to be greater than 0. It has to be positive, and that avoids complex numbers. In other words, if I had an equation like y equals, so let's just say y equals negative 1 in brackets. Now that doesn't count if there's not a bracket there. Okay, brackets negative 1 to the 1/2. That's the same, or sorry, what I was going to write there was if my original function was negative 1 to the x, and in for x I put something like a half. Okay, if I put x is equal to a half and I tried to solve for y, a rational exponent, the denominator of a rational exponent becomes the index. So this is a square root of negative 1. Well, square root of negative 1 doesn't exist. It's an imaginary number. I couldn't graph this. So in other words, every time my exponent has a denominator of 2, my graph wouldn't exist. Well, that wouldn't be very smooth, would it? So that's not an exponential function. And the other rule is that your base cannot be 1. And that's because if you had something like y is equal to 1 to the x, no matter what you put in the exponent, it would always equal 1, because 1 to any exponent is 1. So those are two restrictions that we'll be talking about as we start solving equations. But for right now, you're going to be given bases that work. So the first thing we're going to graph is y is equal to 2 to the x. In Math 60, to graph anything, you are allowed to use a table of values. So we're going to put in values like 3, 2, 1, and so on. So let's do it. So we're going to put in y equals 2 to the 3, which would give us 8. We're going to put in y equals 2 to the 2, which would give us 4. We're going to put in y equals 2 to the 1, which would give us 2. We're going to put 2 to the 0, which would give us 1. And then we're going to put in negative exponents. So if you're not comfortable with negative exponents, in my head, negative exponents means you're in the wrong place. So instead of multiplying by 2, you're actually dividing by 2. And so this would be 1 over 2 to the 1, or 1/2. So if you have 2 to the negative 2, you're actually dividing by 2 twice. So it'd be 1 over 2 squared, or 1 over 4. So then if you had a 2 to the negative 3, same idea, it'd be 1 over 2 to the 3, which would be 1 over 8. So now let's plot these points. So when x is 3, y is 8. When x is 2, y is 4. When x is 1, y is 2. When x is 0, y is 1. And then we get a half, an eighth, or a quarter, and then an eighth. In other words, we're just going down here. What do we notice about this graph? Well, we notice that as the x values increase, so x is 1 or 2 or 3 or 4, the y values are increasing as well. So as x increases, y increases as well. What is the y increasing towards? Well, infinity. What about x? Decreasing. So as my x values decrease, so negative 1, negative 2, negative 3, negative 4, what's happening to my y values? Well, they're also decreasing. So y decreases. But what is it decreasing towards? Well, let's think about if we put smaller and smaller exponents in there. So something like, 2 to the negative 100. Well, that'd be 1 over 2 to the 100. Man, that's a small number. So even if I put like negative 1,000,000, I'd have 1 over 2 to the million. Oh man, it'd be super small, but it would never be 0. In fact, your y values are decreasing towards 0, but they're never going to reach 0. What word from anything you've learned so far represents something where you have a line that you're approaching, but you're never going to reach? Hopefully you're all thinking asymptote. So this graph has an asymptote at y equals 0. All right, the intercept, I didn't put which intercept because we are going to be eventually doing inverse graphs of these, so I just, whatever intercept this has, well, it doesn't have an x-intercept because you can't go through your asymptote. So this has an intercept that's a y-intercept at 0, 1. What is the domain of this graph? Well, the domain is negative infinity to infinity, right? It keeps going in either direction. The other reason is because there's nothing I can't put in for an exponent as long as it's a real number, right? 2 to anything, I can put in 2 to the negative 5.62543, right? It doesn't matter what I put in there, I'm allowed to. So x can be anything. But then what about my range? Well, because I can never cross this asymptote, my y values are always going to be greater than 0. Not square bracket 0, but round bracket 0 up to infinity. All right, so this process that I just did on that last graph, I want you to pause the video and do the exact same thing for y equals 1/2 to the x. What's going to change? What's different? So I want you to graph it, and I want you to fill out the information on the right-hand side. And then if you want to, you could think about these 2 questions at the bottom, but we'll also do them together. Okay, so hopefully you paused, you gave yourself time to write. So when x is 3, I have 1/2 to the 3, which is 1/8. I have 1/2 to the 2, which is 1/4, 1/2 to the 1, which is 1/2, 1/2 to the 0, which is 1, 1/2 to the negative 1, which would actually flip it. So if you have 1/2 to the negative 1, right? So negative exponent means you're in the wrong place, so you can flip it. So this would actually be 2 to the 1, or 2. So if I have 1/2 to the negative 2, I would get 4, and if I have 1/2 to the negative 3, I would get 8. Now if I plot these points, doesn't matter where I start, I'm going to start at my y-intercept, 0, 1, and then to the right, when my y values increase, or my x values increase, what's happening to my y values? Well, they go 1/2, 1/8, 1/4, 1/8, they are decreasing. So this time, as my x's increase, my y's are decreasing towards 0, towards that asymptote, okay, of y equals 0. Then what happens as x decreases? As x decreases, I've got a point at negative 1, 2, negative 2, 4, negative 3, 8. It's going to keep increasing towards positive infinity. So it's the opposite, towards infinity. What's the intercept? Well, it's still 0, 1. What's the domain? It's still negative infinity to infinity. And what's the range? It's still 0 to infinity. But what do you notice about these 2 graphs? So this blue graph is the graph of y equals 1/2 to the x. Just in the interest of seeing them in the same place, I'm going to graph y equals 2 to the x on the same grid. So if I do that, it's going to go to 1, 2, 2, 4, 3, 8, and then the other way, 1/2, 1/4, and 1/8. So it's going to approach your asymptote as the x's get smaller, and it's going to approach infinity as your x's get larger. What do you notice about these 2 graphs? How could you describe these graphs in terms of maybe a transformation, right? So hopefully you're noticing that these 2 graphs are kind of mirror images of each other's. In other words, we call them reflections. It is a reflection across the y-axis. How can I prove that algebraically? Well, if you have a knowledge of negative exponents, right, we've got y equals 2 to the x. That one can't really do much with. I mean, I could, but it's harder. If I have the other one, I've got y equals 1/2 to the x. If I rewrote 2 as a numerator, it would be 2 to the negative 1, all raised to the exponent x. If I use my exponent laws, I have a power raised to exponent, so I can multiply the exponents, and I end up with 2 to the negative x. What I want you to notice is that algebraically, I can see the transformation. This is 2 to the x, this is 2 to the negative x. It's a reflection of the x values over the y-axis. So the next thing we're going to look at is transformations. And so really what you have to know is sort of a base graph, and then you're going to transform there. So you can have 2 different base graphs here. You could have y equals 2 to the x and y equals 1/2 to the x. Or you could write y equals 1/2 to the x as a transformation of y equals 2 to the x. Okay, just keeping that in mind. But the next thing we're going to do is just kind of scale it back a bit and go back to what do we notice about these bases? You know, when the base was 2, my graph grew. We call this an exponential growth graph. It increased as the x values increase. The y equals 1/2 to the x graph, it was decreasing as my x values increase. We call this a decay graph. Why does one increase and one decrease? Well, let's look at some more graphs. So if I look at all of these graphs, we've got y equals 0.4 to the x, y equals 0.25 to the x, y equals 0.7 to the x. What I want you to notice is that this a value is between 0 and 1, right? It's smaller than 1 but greater than 0. What do all these graphs do? Well, every single one of these graphs decays or decreases in its y values as the x values increase. So these graphs, the 0.4 to the x, 0.25 to the x, these graphs decrease as the x values increase, right? They're decreasing graphs. Again, when we get to 4.6, we're going to hold these decay graphs. So the more I use that term, the better. And then for these ones, all of these have a values greater than 1. And when the a value or the base is greater than 1, your graph will increase or it will grow. Okay, other than that, how do these graphs compare? Well, let's look at the asymptotes. Every single one of these graphs, all 6 of these graphs have an equation of an asymptote of y equals 0. Does not change. Doesn't matter if the base is smaller than 0 or greater than 0. What about the domains? Well, there's nothing limiting what I can put in for x, so it's going to be negative infinity to infinity for all of them. The range, they all have y values greater than 0. 0 to infinity. Zoom. And what of the y-intercept? It doesn't matter what the base is. When you put in an exponent of 0, the y-intercept is going to be 0, 1. Zoom. All the same. So it doesn't matter what the base is. The asymptote, the domain, the range, and the y-intercept are all the same. What changes is whether you have a growth graph or an increasing graph or a decay graph, which would be a decreasing graph.